In this lab, we will continue with the trees and ensemble methods. The purpose of this lab is to get experience with the performance of tree-based models and some ensemble methods. In step 1, we read the data from the file of biodegradation data. Then we performed in step 2, we performed exploratory data analysis. We made ourselves familiar with the data set and comfortable uh, uh, in a step-by-step to help us comprehend our data and draw better conclusions and explanations from the results. We plotted one interactive box plot per each variable in the data set. Then we plotted histogram to understand the distributions of each of the variables in the data set. Then we plotted, then we identified all the missing values in the data. There was none. Then in step 3, we performed feature engineering. We created two new variables, NHM, NO, and NNN and CRX3. So we created new column NHM, NO, and that equal to NHM column plus NO column. And we created NNN NCRX3 column and of NNN column plus NCRX3. Then we encoded the categorical variable class using label encoder. So and then we splitted our data into training and test set. That is 50%, about 50% training and about 50% test set. Then we performed scalar on both train and test feature columns to standardize the values. So we didn't perform robust scalar, we just kept it as the default method. Then we developed in step 4, we are developing models. In the task below, we will use train for training and test for testing to understand the performance of the methods that we are going to study below. In the following code, we load the following libraries to perform the task. We need a tree library, and we need random forest, and we need GBM library. So classification trees. In the following code, we fit a really large unpruned classification tree to the training data. There are 22 variables actually used in tree construction as listed in the summary below. Misclassification. So grow a really large unpruned tree. So R equal tree of class. So this is the model that we are trying. Class equal the addition of all the variables. All the feature variables, comma, data equal train, comma, mean deviation equal 0. So we want the maximum amount of branches. Summary of R. So we have a classification tree. The variables actually needed used in tree construction are these 19, 20, 21, 20, 22 variables. So we had a total of 41 feature variables, and out of that only 22 feature variables are being used. And the number of terminal nodes is 44. Residual mean deviance is 0.3607, and misclassification error rate is 0.08523. In the following code, we plot the unpruned tree and try to make the mixed text as pretty as we can. So plot of R, text of R, comma, pretty equal to, comma, all equal false, comma, CX equal 0.6. And we get this. So it's a bit hard to read the tree here, but we can see right on top is SP max BM, which is less than 3.7965 on the left, and on the right is greater than 3.7965. Then for less than 3.7965, we have F02CN, and on the left we have less than 1.5, and on the right we have greater than or equal to 1.5. Then on the left, for less than 1.5, we have SP max L, which is less than 5.0805 on the left and greater than or equal to 5.0805 on the right. Then for less than 5.0805, we have NO less than 1.5, and then for that we have SM68M less than 8.012. Then we have NCP less than 1.5, and so on. Comment: a really large tree fitted on training test showing 22 variables used in tree construction. In the following code, we identify the 3 most important variables from this classification tree. So we have so looks like the 3 most important variables are SP max BM, F02CM, and SP max L. We also have SP pose IBP. So in the following code, we identify 3 most important variables from this classification. R at frame, so display deviance of the frame. So R at frame, square bracket, comma, 3. So this is all the rows in the frame for column 3. And we have these values. Then when we order the frame by deviance, order of R at frame, square bracket, comma, 3, then it orders by the index, ascending order. The bigger values, so the smaller values to bigger values. Then we order the frame by deviance in decreasing order. So let O equal order of R at frame, square bracket, comma, 3, comma, decreasing equal true. And when we print that, we get this. So this is in the deviance decreasing. Print the variables with maximum top 3 deviance values. So R at frame, square bracket, order of 1 to 1 colon 3, comma, and this 1 is for column 1. And in column 1 there is the names of the variables. So SP max BM, F02 CN, SP max L. The leaves are 42 with 42 labels. So the three most important variables are SP max BM, F02 CN, SP max L. And from this tree diagram, we can see those three variables are here. In the following code, we compute the training error. So we need to set the seed because to use the prediction so that the predicted values are the same for the next run that we make. So set the seed of 1, 2, 3, 4, 5, predict the tree on train set, let train dot pred equal predict of r comma train comma type equal class. Head of train dot prediction gives us these 5 values: RB, RB, NRB, 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 NRB. So these are the few first lines of the predicted values. Compute the training error. So mean of the class variable not equal to the predicted class, and that gives 0.0871221. So this is the misclassification rate for the train data. And for the tree, whole tree, the misclassification was 0.08523. So in the following code, we compute the test error. The test error is higher compared to the train set error and also the tree misclassification error rate. Let's have a look at this. So we need to set dot seed of 1, 2, 3, 4, 5. Then we predict on the test data set. Let test dot predict equal predict of 3r comma test type equal class. Head of test dot prediction, we have NRB, RB, 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 NRB, RB. Compute the test error. Mean of test at class not equal to test dot pred is 0.178368. Since we are going, so we can see the test error is higher compared to the train set error. And this is also the misclassification rate. Since we are going to compute the training and test errors frequently below, we write a simple R function named errors that computes both training and test errors and can be reused for any family of models, as long as there is a function to supply the class labels. In the following code, we write fit as the output of growing tree. Let biodeg underscore temp equal biodeg of the square bracket. We have comma, so which means that we are choosing all the rows with column names not equal to NHMNO, NNNCRX3 class underscore encoded. And so when we print names of biodeg temp, we get this. So the misclassification error rate is 0.08523. So when we set dot seed of 1 2 3 4 5 and we grow a really large unpruned data, let fit equal tree of class, and class equal addition of all the feature variables, comma, data equal biodeg underscore temp, comma, mean deviation equals 0. So summary of fit is a classification tree. So we have the variables actually used in the tree construction are 19, 20, 21, 22, 23, 24. 24 variables. Number of terminal nodes is 76. Residual mean deviance is 0.2292 and misclassification error rate is 0.05118. So in the first classification tree, the misclassification error rate was 0.08523. But after excluding the three columns that we added in feature engineering, we excluded. So now we have misclassification rate bit less, 0.05118. In the following code, we plot the unpruned tree and try to make the mixed text as pretty as we can. Plot of fit, so we have this, and text fit, comma, pretty equals 0, comma, all equal true, comma, CEX equals 0.3. So we need to make this more pretty. We can one thing we can do is make this tree bit bigger. Comment, a really large tree showing 24 variables used in tree construction. See, 20, 21, 22, 23, 24. In the following code, we write a function that that uses fhead.tree open and close bracket that uses fit and computes the class labels for a data set. So let fhead.tree equal function of fit, comma, data and curly braces set.seed of 1 2 3 4 5. Let pred equal predict of fit, comma, data, comma, type equal class. Return pred, close the curly braces. In the following code, we write a simple R function named errors that computes both training and test errors and can be used for any family of models. So let errors equal function of fit, comma, fhead.tree, this function here, comma, train, comma, test, then open curly braces. So set.seed of 1 2 3 4 5, train set error, let a.train equal mean of fhead.tree of fit, comma, train not equal to train at class. Test set error, let a.test equal mean of fhead.tree of fit, comma, test not equal test at class. Retain column bind of train dot error equal a dot train, comma, test dot error equal a dot test. In the following code, we demonstrate that errors and fhead.tree works correctly for the unpruned tree. From our demonstration results below, we conclude that errors and fhead tree works correctly for the unpruned tree. Since the tree error and test error are same from using both the functions, call the function errors on train and test sets. Errors of fit, f head.tree, train, test gives us train.error of 0.05113636 and test.error 0.0512334. In the following code, we manually compute misclassification error for train and test set using fhead.tree opening close bracket. Classification table for train test, let t.train equal with bracket train, table of fhead.tree of fit, train, class. So this is a table of fhead.tree fit, train, class. So that gives a classification table. So where the rows represent the prediction, the result from the fhead.tree, and those are the predicted class, and the column class represent the observed, the train class column values. And we have the prediction equal to observed 319 values for NRB and 182 values for RB. And for NRB, not equal, for the classes not equal, the predicted and the observed classes not equal, we have 14 and 13. Manually compute train set error, sum of t.train, bracket column of t.train not equal to row t.train, that gives 14 plus 13 equal 27, and divided by sum of t.train, that is the sum of this classification table, and that's 0.05113636. Classification table for test set, let t.test equal with test, table fhead.tree of fit, test, class. So the rows represent the predicted test values from the model fit, and the columns represent the observed class values. And for the prediction not equal to class, NRB is 353 and RB is 147. And where NRB is not equal to RB is 13 and 14. Manually compute test set errors, sum of t.test of square bracket column of t.test not equal to row of t.test divided by sum of t.test equals 0.0512334.